5.7, the ideal gas law. For this one, work all the problems that are indicated. This point, the problems for, like, say, AP, honors, general are a little different. Especially in AP, there's a lot of applications to this gas law that we'll be doing. So, just what it tells you either on the assignment there or on the worksheet for your assignment. Okay, now let me see. First of all, I like to always bring this in. If you go back to right before section 5.5 in your notes, right before that is a picture of Avogadro, and there he is, Avogadro, Amadeo Avogadro. And what does it say there? His hypothesis? Well, before I tell you his hypothesis, I'm going to show it to you right here. So 5.7 with the ideal gas law. Here's a neat thing. Okay, so let's just say that we have 3 balloons, and all of them are blown up exactly to the same size. Didn't do too good of a job there, but let's just say that that's probably about 2 liters. Just say the volume is 2 liters. The volume here is 2 liters. And the volume here is 2 liters. Now let's say the temperature is all 25 degrees Celsius is a good room temperature. Of course, that would be 298 Kelvin. We're not going to do anything with the numbers. I'm just using them to show you they're the same. And let's just say the pressure is standard pressure. The pressure of that atmospheric barometric pressure, 1 atm, 1 atm, 1 atm. Okay, so in the first container, let's just say that we have, let's see, helium would be good, carbon dioxide, yeah, maybe hydrogen as well. We'll just do that way. Or, well, yeah, we'll do it that way. So we have hydrogen, but H2, that's 2. Helium, carbon dioxide, and maybe we'll use oxygen in that case. I'll use oxygen. So helium, oxygen, and carbon dioxide is used to blow up each of these balloons. Same, all of them are the same volume, same temperature, same pressure. Now, think about how large a helium molecule is. If you look at the mass on the periodic table, it says it is 4 grams per mole. So 4 AMU. That's 4. So let's say it's like maybe this large. We'll just put I'll draw a little circle like that. It's gonna be, I'm going to make it too large. Let me do it smaller. So let's say helium is that large. Well, oxygen, this is 4 gram per mole. Okay? Oxygen is 16 plus 16, that's 32 gram per mole. So 4 times what is 32? 8 times bigger than that. So wow, how can I do that? I guess something like this might be the size of it. And then for carbon dioxide, I'm going to put, it's going to be about 11 times larger than that. So it's even going to be even larger than that one. And actually, well, if I did it right, it would be O2 would be 2 of these together. There'd be 2 molecules in there. Well, okay, we get the idea though. Something like that. Okay, the CO2 is like carbon with O and an O. So it should be larger. Close to the size of this one, but larger for sure of all of them. Okay, so if you had to think about like gumballs, a gumball machine, which gumball machine, if you filled it up, would hold the most? If they were solid gumballs, well, you'd say, well, for sure, helium's going to fill up a lot more. Who's going to have the most gumballs? Helium gumballs will be full a lot more because they're so small. This will be a lot less because they're larger, and that will be somewhere in the middle. That's what you would think. But what Avogadro does is what you would assume to be true is not true in this in this example. There's a word, I couldn't think of what the word is. If it comes back to me, I'll tell you later. But a scientific word I was going to use. Anyway, so what happened was Avogadro studied a lot of the gas laws, the early gas laws. This is before they knew the periodic table. They didn't know anything about the periodic table, where elements were. They did not know this arrangement at all. They just knew that some things were elements, but they didn't know all this yet. So what Avogadro looked at all the data, like probably of Gay-Lussac, probably of even maybe Dalton, a bunch of other scientists around, or maybe I'll just look at the years of their lives, whenever they were. And he noticed something amazing. he said, you know what? According to the data, it appears that all the volumes have the same number of particles in it. So what his Avogadro's hypothesis or his law says, equal volumes of gas, if they're all the same volume, at the same temperature and pressure, will contain equal number of particles. That's amazing. Now, we can't really think about that. We look at my picture and you say, well, that's really large, that one's really small. How can this have the same number of molecules as that? Well, first of all, what I drew is too large compared to the size. Atoms and molecules are really small. But the main reason is this. I'm going to show you. It's because it has to do with how they move around and their energy and the space they take up. We'll talk about this when we talk about another scientist. It's called Graham's law. We're going to do it later on. But here's a way to think about it. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. 1, 2, 3. What did I just do? Okay. Here's another way to look at it. At the same temperature and pressure, in a volume of gas, there are the same number of parking places. That's another, or parking spaces. Say that they all have, what did I make there? Well, I didn't do a good job of drawing that one, but they all have about 1, 2, 3, 4, 1, 2, 3, 4, 5, 20. 20 parking spaces. Now, it's round, so some go around the other side, we'll say whatever. But 20 parking spaces. Each one has 20 parking spaces. If you had 20 parking spaces, like say outside the school, I would say in front, so there's 100. Well, think about it. 100 parking spaces. Make it that way. 100 parking spaces. You could either fit 100, the smallest car you can think of, like those stupid little smart cars. You could have 100 smart cars right there parked, one in each space. That's the rule. One per space. 100 of those, all right? Or you could have 100 of like a really large car, like say like a Hummer, okay? You could have 100 of those, and that would take up like all of it. A Hummer would take up almost the entire space in there. I don't know how to draw it so good there, but you get the idea. Well, the point is, if I color this all in, they're both going to have the same number of molecules. Well, I didn't completely draw one all the way. They're going to have the same number of molecules, but what happens is, as you'll see later, the way they move around, that these move around really fast and fill up their little space as they go around, collide. Now they move around, they leave their area, but just to get, if you get a freeze frame of it, these don't have to move as much at the same temperature. And we'll talk about that. I'll come back to that same example when we get to Graham's law. But anyway, that's what Avogadro said. Equal volumes, if the pressure, the volume, and the temperature are equal, then the number of particles will also be equal. So that was a major, major breakthrough, because now for the first time, there is a mathematical relationship between the number of particles and temperature and volume of gas. So that's amazingly significant. Because of that, this equation was able to be developed, PV equals nRT, called the ideal gas law. Now, a couple of things about this word law. In physics, they really hate it if we use the word law, unless it is a law. Mathematically, if you can't prove it math, it's not right, not science. Well, I do agree with that, but I'll just say one thing, that on Earth, on our normal, everyday temperatures, pressures, every conditions you'd be in, this law does work. But Avogadro's law is not perfect, but it is perfect. It's good for Earth and all this. There are some strange situations, really, really high pressures or really, really cold temperatures where this thing starts to fail and it doesn't show, and we got to make an adjustment for it. But Avogadro was correct. So you can't really call it a law. It's really better to call Avogadro's hypothesis, okay, just to be safe, because it's not 100% true. When it's not true, though, we can tell you how to fix that so it can be. Now, the ideal gas law should be called the ideal gas equation, and also again, there is no such thing as an ideal or a perfect gas. But anyway, okay, so in the PV and RT, pressure usually will be in atmosphere, but it can also be in millimeter mercury or torr. But usually in atmosphere, you'll see why in a minute. The volume it always must be in liters, always. Temperature, you already know that one. It always must be in Kelvin. And N now is the number of moles. So now you get to put stoichiometry a little bit into this. But We don't actually get to stoichiometry, gas stoichiometry, for several more lessons. So don't be afraid of that. But you are going to look at the chart to get gram to mole, mole to gram. That's about all. It's not going to be too bad. All right, now, what in the world is R? Okay, well, in a math class, if we gave you that symbol, you'd say, what is that? Oh, it's pi, okay? And you say, well, pi is a constant, 3.14. If I use area, pi r squared, or circumference is 2 pi r. You've seen that before. You know pi is a constant. Well, it turns out that in physics, there are many, many constants. And in fact, another very famous, a famous one would be E equals mc squared. And you know that the constant is c, which is the speed of light. Einstein's equation, energy, mass times speed of light squared. Okay? That's a constant. So if you put in the amount of any mass, you can find the energy, or any energy, you can find the mass corresponding to it. Okay, well, another one is Newton's law of gravitation. There's something called the universal gravitational constant. Okay, and if I know the mass of one planet and the mass of another planet, or how about if I know the mass of the sun, I know the mass of a planet. All I gotta know is how far they are apart, and I can tell you what the gravity pull will be on each one would be. Or how about between your body and the Earth? I can tell what your pull, what the pull on you will be from the Earth if I know how far you are from the Earth. As long as I know your mass and the Earth's mass, that means I can figure out your weight at any given point, any height. You do that by using the universal gravitational constant. Why am I got off the subject, but oh well. Okay, well, R is called the gas constant, and that number is equal to 0.0821 liter atmosphere mole Kelvin. This is the way we write the unit. It looks kind of strange. Don't try to understand it. Just think about this. This is a number and units that makes the rest of it true. P times V of a gas will always equal N times T of the gas times R. As long as R is in there, that makes that side, left and right side, equal to each other and true. Another way to write this gas constant is 0.0821 liter atmosphere mole -1 K -1. Now this is more for the advanced, but because those are like over on the bottom of the denominator, mole -1 K -1, you said as well. And I'll go and add this on 62.4 liter millimeter of mercury mole in Kelvin. Now, if your unit is in millimeter of mercury, that's pressure. If your pressure is millimeter of mercury or in torr, then you can use this number instead for R. Or you can just convert your pressure into atmospheres. Most people say put it in atmospheres. Most books use atmospheres. Surprisingly, a lot of times in the general chemistry, they also have another one, which is 8.314 liter kilopascal mole -1 K -1. So I just tell you, if the pressure is in kilopascal, millimeter of mercury, or torr, you can use this if you want to, this shortcut, R value, or just change it into atmospheres and do it. It turns out that millimeters of mercury and torr, this is a lot more practical in a lab to measure with that. You'd see why for gases. It's a lot more easier, like it makes more sense than using atmospheres. Okay, so here we go. Let's try and do a problem. And it says, number 1. Okay, it says a sample. Let me go here. Not a sample, I got the wrong one. All right. What will be the volume in liters of a 2-gram sample of nitrogen gas at STP? I kind of don't want to do that one. I don't really like the STP thing a whole lot. Well, I'll do it anyway. Okay. And B says what will be the volume. Okay. B is actually a lot better. Let me do B first. I'm going to do B and then come back to A. All right. I've got 2-gram sample of nitrogen. 2.00 grams. Nitrogen is N2. Okay. Now they give me what will be the volume in liters of 2-gram sample of nitrogen gas. I'm doing B at 25 Celsius and 3 atmospheres. 25 Celsius, that's a temperature, right? And 3 atmospheres, that's a pressure. And, okay, So let's think about this for a minute. They want you to find the volume. They want you to find V. Okay, how does this equation compare to what we've been learning so far? All the other equations we got. Now you get them all in your mind. Okay, well, whenever you read a problem and it says something about pressure, volume, temperature, if it says pressure, volume, temperature, and here's the new pressure and the new volume, what's the new temperature? Well, that's a before and after problem. And so you think usually that's going to be the combined law. PVT equals PVT. Well, if you here in a gas law problem, pressure, volume, temp, and they give you grams or moles, or if they ask you for gram or mole, then you know you got to use PV and RT because this is going to link it to moles. So, I mean, you could also look at it as PV over T NT equals R if you wanted to. Well, that's kind of confusing for some. I wouldn't worry about that, but you could look at it that way. But anyway, okay, but if you say something about grams, then gram or mole, use PV and RT. Just remember that. So the first step I got to do is change gram to mole. So let's find out how many moles I've got. Let's go to mole of N2. Now, I put N2, did I say Hofbrinkel? I didn't tell you, but I told you they pop up a lot, and especially in this chapter where the gas law chapter is. So N2. All right. What is the mass of nitrogen? Look on the periodic table, and it says 14.01. But since it's N2, that means 14.01 times 2, which is 28.02. Okay, gram to mole. 28.02 is grams. And remember, put 1 by mole. Okay. Now, 2 divided by 28.02 is 0.0714 moles of nitrogen. Okay. Now, we just did all that work. I don't want to erase that yet. But we didn't find the answer yet. Okay. I was going to try to put, I can fit it here. PV equals nRT. Now I'm going to plug the numbers in. 3 atmospheres. So I'm going to put, do all like I did in the last gas laws I showed you. First, write down the equation. Then show everything plugged in with the correct units. 3 atmospheres. The volume is, we don't know the volume. We're trying to find V. Okay, the moles are 0.0714. This chalk is starting to go. And the temperature is 25 Celsius. Now remember what I told you? 25, don't even write it down there. Go on and Kelvinize that baby. 273.15 plus 25 is 298.2. So 298.2 goes here. And you know what? I'm sorry. I didn't put my R in there. Oh. Well, 298.2. I better just do it this way. I could have put R at the end, but oh well. 298.2 Kelvin. Okay. And here is R, which is 0.0821 liter atmosphere over mole Kelvin. Now, I told you pretty much you ought to just stay and use that R value. Okay. If the pressure is in atmosphere, then that's the R value you'll use because it tells you atmosphere. Okay? Now, if the pressure is in millimeter mercury or torr, you can use that one or the one for kilopascal if that pops up. But, okay. Oh, boy. Let me find another. Okay, here's some chalk. Okay. Now, actually, I want to use a different color. Okay. Now, here's a great thing about the ideal gas law. When you put the R value in, it tells you what units you have to have. So, hey, it works so great. If you thought, I accidentally put Celsius, I was going to put it above it. Sometimes I write it above there just so I'll know, but I don't put it inside the parentheses, okay? Sometimes you might have Celsius accidentally. Well, watch this. Anything you see twice, Kelvin and Kelvin should cancel. Good. All right, that means I did that one all right. Mole and mole should cancel. Atmosphere and atmosphere should cancel. But liter doesn't because my answer is going to be in liters. So, and sometimes you might have liter and milliliter on there, so you might have to convert. So, liter to milliliter is a common thing that would happen in a lab. And Celsius temperature is almost always in Celsius. I don't know why this thing likes to move so much. Okay. All right, so you might see some conversions in this chapter. Okay, so 3 times V equals, and I'll multiply these, 0714 times 0.0821 times 2, 98.2. It's 1.75. Okay. Now, let me double 01. This is 14 times 821 times 298.2. Yes, that's right. Divide both sides by 3. And the volume equals 0.583. And it's liters. Yeah, but it's up there. Just in the very last step, make sure you have it written there. 0.583 liters. Okay. Now, nitrogen gas at 25. Compressed cylinder. Okay. You know, I didn't do letter A, but I can just show you really quickly what would have happened to A. It's a pretty simple thing. On A, if I just go backwards, it just said, what's the volume in liters of 2 grams sample of gas at STP? So that means now my temperature, STP, standard temperature and pressure. Standard temperature is 273.15. Standard pressure is 1 atmosphere. So that becomes a 1 right here. And standard temperature is 273.15. So that's all that will be different. I don't think it's really needed much to do this problem because, well, I just did it for you real quick to show you A because I know that's 1. 1 times V makes the answer really simple to get. The volume will be multiply these. Just make sure standard temperature is 0 Celsius or 273.15. And as I told you, standard temperature is kind of less important now than it used to be. But you might hear the term, especially in general class, you might hear that. Looks like 1.60 liters. Is that right? Okay, 0.0714 times 0.0821 times 273.15. Yeah, 1.60 liters. Okay, now, at this point, for the general classes, that's all you have to know here, and you're going to do the problems that come up. But for the AP, there's going to be a couple more things I have to show you. So I'll have to put another part on this right after this.